Okay, now let's talk about the content-based filtering in detail. Okay, so what we need is some information about variable items. So we need content. Okay, the system should understand the content. Okay, and some sort of user profile describing what the user likes or the preferences. So this user profile can be updated based on the history of users' items, users' selection, or sometimes we can ask the users to give us some descriptions. So if you register kind of internet dating page, then you have to describe something about yourself, what you like and what you do in weekend, something. So you have to provide lots of information about yourself, and then the dating website will use this kind of information to find your partner. So this content can be given by the users directly, or if you click something, then the system can learn about yourself. Okay, but anyway, the system will build up a user profile, and then the task is to learn user preferences, as I said, and locate or recommend items that are similar to the user preferences. Okay, so as I said, there is no serendipity. Okay, so unexpected joyful event. And the item descriptions are usually automatically extracted. Okay, as I said, based on the history, then we can extract those information. The item descriptions are usually automatically extracted from the data. Okay, so for example, if it is article recommendation, then from the article that we have to extract some information, then this information should be structured. When we compare two items, then we need to calculate some distance or dissimilarity. So to calculate the dissimilarity between these two items, then we need some vector, right? And how can we extract this vector from items? So that's important thing for content-based filtering. Okay, simple approach. So we have to compute the similarity of an unseen item with the user profile. Okay, based on the keyword overlap. If it is article. Okay. And the standard measure is TF-IDF. Okay, that is the standard measure. So it's traditional measure. Recently, we can use something better, but TF-IDF is quite a traditional, simple approach, but is working well. Okay, so TF measures how often a term appears. Okay, is term frequency. And IDF aims to reduce the weight of the terms that appear in all documents. So this one says inverse document frequency. If one word appears in all the documents, then that word is not an important word, right? So TF says if one term appears a lot in a specific document, then this term is important. But IDF says if this term appears everywhere in all documents, then this term is not important. Something like is, or a, or on, or are. These words are not important because it appears in all documents. Okay, but something like economics. So this word appears in a specific document, right? And if this word appears a lot in a specific document, then this word is important. Okay, so we multiply this TF and IDF. And when we calculate TF, we get the frequency and we normalize this frequency with the max. Okay, and when we calculate the IDF, and this one is the number of all the recommendable documents, and this one is the number of documents in which keywords I appears. So we actually check how many documents have this keyword in it. Okay, and then we calculate TF-IDF of the item and find not yet seen neighbors of the items. Okay, then we recommend this not yet seen neighbors of the item. Okay, so this is one example of content-based filtering. So when the item is based on the article, okay, then we can extract the feature vector of this item and then we can compare. And TF-IDF is one way to get the feature vector of this article. Okay, then what about the movie? Okay, then when we calculate the dissimilarity, then maybe we can use actors and actress and director and genre and so on. And also we can use some, we can use some other information to check the similarity between two movies. Okay, and what about images? So there's no text there, then probably we have to extract some features from images to compare the dissimilarity between two images. So if we have different content, different types of content items, then we have to come up with the new recommendation system. Okay, so let's say we have a recommendation system for images, and then we cannot apply this recommendation system to a news article, right? Because this content, the type of content would be completely different. So it depends on the application, it depends on the data type. So every time you have to build up new recommendation system. That's another big problem here. Okay, now let's talk about the collaborative filtering in detail. And it is the most prominent approach to generate recommendations. Okay, and it can be used by a large commercialized e-commerce site. And it is well understood, and various algorithms and various variations exist. And it is applicable in many domains. That's the beauty of this collaborative filtering. That's why people use collaborative filtering more than content-based filtering. So once you develop one collaborative filtering in one specific domain, then we can apply that filtering to other domains so easily, because it is not based on the content. So as long as we have a user and the items, user item matrix, then we can apply this method to any kinds of domains. Okay, and it uses the wisdom of the crowd to recommend the items. So it is based on the crowd. And the basic assumption and the idea is that users give ratings to catalog items implicitly or explicitly. So it means users give feedback. Okay, so without the feedback, we cannot apply collaborative filtering approach to recommendation system at all. So we have a feedback, okay? And then the next assumption is that customers who had similar taste in the past will have similar taste in the future. That is assumption. So the important question is how to calculate the similarities between the items. Okay, that's the main point of collaborative filtering. And we can actually use a couple of different similarities. First one is Jacquard distance. Okay, so let me give you an example of this Jacquard distance with this table. So we have 7 items and we have 4 users, and let's calculate the distance between A and B. Okay, so we have, let's check this intersection. So we have one item, okay, that A and B both like. Okay, that is 1. And how many items do we have? A likes item 1 and item 6, and B likes item 1 and 3 and 4. So union says 1, 2, 3, 4. Okay, so 1 minus 1 over 4 is 3 over 4. That is the distance. Okay, what about A and C? A and C. So how many items we have in union? 1, 2, 3, 4, and 5. Okay, we have 5. And how many items that both like? Nothing. Okay, 0. And 1 minus 0 is 1. So the distance between A and C would be 1. Okay, so it says A is closer to B than C. So we can actually measure the distance based on this Jacquard distance. Okay, and the next one is cosine distance. I think you already know how to calculate this cosine distance. You just consider this as a vector and another vector and another vector and another vector. So simply we actually calculate the cosine distance between these vectors. Okay, that's easy. Or we can use Pearson correlation, or if you want, you can come up with a new distance. You can design your own distance. Now we know how to calculate the dissimilarity between the users, so we can find the neighbors. Okay, then we can recommend what they like. So in this slide, this is target user, and then we found 3 users as neighbors. Okay, so which means they like what I like. Okay, then they like other movies too. So she likes Spider-Man and Dune and Saving Private Ryan, and this guy likes Dune and Saving Private Ryan, and this guy likes this one too. And so when we recommend what they like the most. So in this figure, they like Saving Private Ryan the most. So we recommend this one as the first movie, and this one as the second and third and fourth. So basically, we find the neighbors and then we check what these neighbors like. Okay, and then we recommend the video that the neighbors like the most. That's the main idea. So in the previous slide, we talked about the concept of collaborative filtering. And now in this slide, we're going to talk about the detail. Okay, so given an active user Alice, let's say Alice, and an item P not yet seen by Alice, then the goal is to estimate Alice's rating for this item. Okay, this is how we recommend one specific items to Alice. Okay, then find a set of users who like the same items as Alice in the past and who have rated item P. So we have to find the neighbors. Okay, and then use the average of their ratings to predict if Alice will like item P. And do this for all items Alice has not seen and recommend the best rated. Okay, so let's take a look at this table. So we have 5 items and we have 5 users, and Alice is the target active user, and we have other 4 users. And Alice have watched 4 items, and then she actually gave feedback about these 4 items. And we can check the similarity between Alice and users based on these ratings. So just consider this as a vector 5, 3, 4, 4. And this one is quite similar. And this one is slightly different from Alice. And this one is different. And this one is different. But we can calculate the similarity. Okay, then user 2 gave rate 5 for item 5. Okay, then the user 1 and 3, 4, they gave some rate. Okay, then the question is, what would be this? Okay, so if we can estimate this value, then we know how much Alice likes item 5. Okay, then let's say we have another item and another item and another item. Then we can do this for all the items that Alex didn't use yet. Then based on these scores, then we can recommend the best item, right? Okay, then we can use this similarity as a weight. And then this one is the rate from other users. Okay, and then we use this term to adjust the bias. If similar users have a high rate, then this one will have high rate, high score. So that's the basic idea. And in the previous slide, we used the user-oriented neighborhood method, but sometimes item-oriented neighborhood method will be easier. Okay, so the basic idea is to use the similarity between the items, not users, to make predictions. So look for items that are similar to item 5. Okay, so in this case, item 5 has labels here. And based on these 4-dimensional vectors, then we can find the similar items. This one and this ones are quite similar. Then this one has 5 and this one has 4. Then what would be the number in this cell? So basically the same thing, right? So in this matrix, in the previous slide, we use the vector in this direction, but in this slide, we use vector in these directions. Okay.